Hello, today we will discuss introduction to process graph or P graphs. Before I start, I'd like to acknowledge the author of these slides, Professor Michael Angelo Promentilla from De La Salle University, Manila, Philippines. This is the outline of the lecture. First, we will have an overview of the P graph, then a demonstration, and for the last part, you will do a case study of a green supply chain. First, we will move on to the overview of the P-graph. The P-graph or process graph framework is a graph theoretic framework for process network synthesis. So what is a process network? Basically, any um, any process that you can represent in a network. For example, you have your process flow diagrams that have different raw materials, different pathways to produce the products. So if you have a network representing different routes to produce a result or not just product but any final output. So that can be solved using the process network synthesis, and the bigger framework is able to is a tool in solving process network synthesis problem. So it was developed by Ferenc Friedler and Liang Chen Fan and coworkers. The advantage is the computational efficiency and automated generation of alternative structure. And later we will give details on how it's able to increase the efficiency of computation. Um, it's a bipartite graph. The bi here refers to the two types of nodes, the material and the operating node. So basically, it's as simple as a simple representation using two types of nodes, the material and operating type nodes. So the material is represented by circles, and the operating unit is represented by a rectangle. For example, we have an operating unit right here. Um, a boiler is the rectangle, and we have the flows. So you have the flow right here for power, zero point zero 0.01, the fuel oil, you have the liter per second, and then for the water, treated water, liter per second, and the heat kilowatt. And you also have the raw materials um, right here, right, and also the product. Okay. Uh, so it's able to unambiguously represent industrial process. As you can see here, these two, the process on the left and the right are uh, made using P-graph. So it's able to differentiate between the two. Okay. As mentioned, there are two types of vertices, the operating unit. And under the material type, there are three. We have the raw material, represented by inverted triangle, the intermediate, represented by solid circle, and the product, represented by a dotted circle. So let me compare the conventional graph representation with that of the P graph. So above we have the presentation of a process network. We have this one, and from O1 to O2 becomes O3. What is O1 and O2? Are these operating units, right? And then we also have B, C, and A. Are these all operating units? So what about this one? Is this an operating unit or is this a material? So the conventional graph representation is quite confusing, but in P graph, um, it's able to clearly represent the process network. So here we have three operating units and we have intermediates. Here we have three operating units and we just have one intermediate. So this is actually the part right here. So it's able to differentiate um, the representation of a process network. So here we have 3 operating units, but with 2 materials, but in this one, we have 3 operating units and 1 material. It's based on 5 axioms. The first one is every final product is represented in the structure. Um, and then a material represented in the structure is a raw material even only if it's not an output from any operating unit represented in the structure. So it's a raw material if it does not have an inflow, right? For example, this would be a raw material, this one, if it does not have any flows entering that material. 3. Of every operating unit represented in the structure is defined in the synthesis problem. For any operating unit represented in the structure has at least one path leading to the product. So it just means that the operating unit should not be isolated from the product. So there should be a path going to the product connecting the operating unit. And if a material belongs to the structure, it must be an input to or output from at least one operating unit represented in the structure. So you have to follow these axioms in building your process network. Otherwise, if you do not follow it, PGAF would automatically remove the invisible structures. And just like in Lingo, our mathematical programming software, it has solvers that, and these solvers are able to determine the optimal uh, solution. In PGraph, we have algorithms. We have the maximal structure generation algorithm, or MSG. It generates the superstructure. So please remember what's a superstructure. Basically, it's the network that contains uh, all possible combinations. And then we have the solution structure generation, or SSG. From the superstructure, it um, identifies the uh, feasible subset of networks. Okay. Later, I will show in detail what the SSG does. Okay. Next, we have the accelerated branch and bound. So this is a solver, and it's also the branch and bound is also being used in mixed integer linear programming or mixed integer problems, mathematical problems. But in PGraph, it's enhanced with the SSG to eliminate infeasible and redundant solutions. So that makes it an efficient solver because it skips the infeasible and redundant solutions. Next, we have let's move on to the MSG and SSG. Uh, I, this is the algorithm of the MSG, uh, but we're not interested in the details of that. In case you are interested, then you can try to read the mathematical representation of the algorithm, but as beginners, I suggest that we move on to the next slide. So for example, here is our superstructure. We have the A and B as final products. We have raw materials, E, J, K, G, L, intermediates, F, C, D, 5, and we have 7 operating units, 1, 2, 3, 4, 5, 6, 7. So this is the superstructure because it contains all possible networks. As you can see, there are many paths to generate product A. We can start with raw material J, pass through here, or we can start from K, pass through here, and go there. So there are many possible solutions to this network to produce A and or B. So this is a once you build your structure using pgraph and you click on the button of the MSG algorithm to solve the problem, okay, you select MSG algorithm and click the solve, it will give you the error-free superstructure. Okay, pgraph is shown to have 30% improvement over erroneous mathematical programming model. Okay. Next, you go to the SSG algorithm. So you can also select the SSG algorithm from the pgraph, and this is the mathematical detail for that. We will not discuss this in detail. So after clicking the SSG or selecting the SSG algorithm and solving the problem, from the initial superstructure here, as you can see, SSG is able to enumerate the feasible solution. So to produce A, is solution 1, solution 2, and so on and so forth. These are unique structures that produces the final product. So we also have cases wherein there are two products, there are cases when there's just one product, and so on and so forth. Okay. Um, and it's able to remove the infeasible and redundant structures. Therefore, it reduces the problem size to manage the combinatorial exclusion. For example, if you have a 35 process example that has three, the pgraph is just able to narrow it down to 3,465 networks compared to the 35 times 10 to the 9 or 35 billion networks. For example, it's able to narrow down the reaction pathways to 71 out of the 31 billion possibilities. So because of that, the accelerated branch and Brown is able to focus on just small subset of solutions and not run throughout that billions of other solutions that are redundant and infeasible. So that's why it's computationally efficient. Okay, let's skip this slide. It's basically uh, they're trying to introduce pgraph in the chemical engineering curriculum. And to download pgraph Studio is the software that you can use to solve the pgraph network. I mean, use the pgraph framework to solve your process network synthesis problem. But this is not updated. Basically, you just have to go to Google and search pgraph Studio, and then you download it. I think it's the updated website is pgraph.com, right? So pgraph Studio is the software that we're going to use. And these are some developments in the pgraph research area. Why use pgraph? What's the advantage over the mathematical programming solvers or softwares? Because the network structure, as you can see, pgraph can visualize the network structure. Unlike in Lingo, we're just uh, given the solutions as numbers. There's no visualization. But in pgraph, there's visualization, and the network structure in pgraph has the strongest influence on the performance. That I mentioned earlier, that the SSG is able to remove the redundant and feasible network structures, thus improving the performance. And aside from that, it automatically gives gives alternative solutions. So not just the optimal solution, but also the near optimal solutions. In Lingo, you have to set that in the preference tab, you have to set it to generate alternative solutions. Um, but the advantage of pgraph is that these solutions are also visual in nature. It gives you the structure of the alternative solutions. And why is this important? Because sometimes the alternative solutions or the suboptimal or near optimal solutions are better than the optimal solutions. these are the applications of pgraph. Basically, if you have a process network, then you can use pgraph, like in chemical reactions, industrial plants, parks, and supply chains, etc. And they're also trying to apply it in ecosystem, networks, and artificial intelligence, etc. Next, we move on to the pgraph demonstration. So at this point, I will open the pgraph studio. Okay, hold on for a while. Okay, I forgot to record. Let me just, uh, okay, let's start again. So this is uh, the Graph Studio. So you have the different type of nodes here. You can click and drag like that, or you can click here, and you have the different types of algorithm. You can select the algorithm and click the solver. So you also have so let's try a very simple network. Material, operating unit, and the product. Let's connect them with a link, flow, click once, click another time, click once, click another time, right there. Okay, so if you want to change the property, so you have to go back to the pointer and click the node. So you can change the properties here. So we have price, flow, max, and operating unit. So you have the properties here, as well as for the uh, product. So you can also modify from the preferences, the problem settings, the defaults, money unit, time you can set for years, default unit, uh, also here in the default values, the payout period. This matters if um, say you have a capital cost and there's a there's an investment cost. So the payout period matters if you are because the P graph minimizes the total cost. So yeah, it concerns you if you want to change the payout period if um, the investment calculation matters. So you can modify there. So let's try to put values. For example, we put a value of €1 or let's see the default unit is tons. Mass tons. Okay. Set. And then so it did not change. You have to before creating. So anyway, let's proceed with megawatts. So €1, €1, and then let's try for operating unit. You have a fixed investment. Just a very simple problem. So it means there's a €10 fixed cost, and for every flow, it would cost €5 for every material flow that goes out of this operating unit. And for the final product, let's put a price of 10 and a max of flow of 10. Alright. So let's try to solve this simple problem by firstly MSG or the superstructure. So this is the superstructure. So you can see maximal structure. Because our problem is simple, our network simple, obviously we just have one flow. How about SSG? Well, let's try to solve SSG. Click here, you see there's two solution structure. One is This one, meaning a solution is not produce any product at all. The other one is produce the product or using this network. Let's try ABB, accelerated branch and bound. So once we do this, it will optimize the cost. It will minimize the cost. So again, clicking here, you would see there are two feasible solutions. One is the solution one is right here, okay? Uh, and then the solution two is not produce anything. All right, so how can we download the results? So we basically can click the structure that you would like to investigate, click file export, Excel, detailed. Okay, let's try this. Export, okay. And then I'll open the file and then show you. Okay, hold on. Okay, hold on, please. There. So this is the solution. So what can you see? Let me remove that. So raw material, the flow is negative. Okay. And then for product material, the flow is positive. So the cost here is 10. Total cost, the uh, so since the price is 1 times 10, it's 10, but and then here the price is 10 times 10, which is the flow. You get 100. So subtract it, you'll get negative 90. Okay, so what does it mean? Uh, a negative cost means profit. So it means that you're able to profit from the product at 90. So your profit is 90. Because a positive cost means it's an expense. Okay, so what else? Here. So under the flows, the more negative it is, the more profitable the system is. Okay. And then operating units. So take note that the default time is hours and the default currency is euro. Okay. Huh? If you want to change something, you have to go back to the original problem. Hold on. I will show the graph. So, for example, you want to change something, so you have to pick the original problem here. Okay, original problem. Then, okay, so for example, here you want to change something. Hold on. Okay, hold on. Okay, so I fixed the network right now. I chose tons. Okay, And then please see so you can follow. I will click each of the nodes so you can follow it on your own. So here, raw material, copy the object properties, operating unit, make sure that we're the same, and also this one. Okay. For the flows, you can actually set the rate, but let's use the default. Okay. So after that, you can use the ABB to solve it. And then solution structure one. Let's export the Excel detailed. Okay, I will open it. Share with you. All right. So here the same answer as before. I just changed the unit to tons. So let's move to the next example. What if there is what if there's an intermediate produced by another operating unit with significant cost contribution? So let me open that. Uh, okay. So on your own, please try to copy this one. So I will click one by one. Okay. So by the way, I changed the from the preferences, change the money unit to MU. Please copy everything right here. And also the L period is 10. So copy here for the raw material, operating unit 1, please copy everything. The product, okay, please copy here. The resource, and then for the flow rates, just one. Then add a resource limit. Okay. So because our goal is to produce an intermediate product with significant cost contribution. So there's resource limit here and put a max flow and required flow. And then operating unit 2, copy this, intermediate, copy, copy right here. So as you can see, um, from the measurement of the intermediate is in megawatt. Okay, it's in megawatt. And see here, it's megawatt. So the raw material is in mass. Okay, so please copy that. You can change it right there. Let's try to solve this problem. First, the MSG. So this is the maximal structure. Next, the SSG. We have two structures like before. And then ABB. So we have solution structure 1. Okay, what do you observe? Uh, there's already a flow right there. And then let's try to um, hold on. Let's try to export the Excel to see the results. Okay. So these are the results for that. As you can see, there's an intermediate flow, and there's a, so we have the intermediate has no cost right here because you did not put any cost. Let me go back to the original problem. So see, you can, when I click here, you did not, we put the, hold on. Okay, so let me just share with you uh, the slides. So basically, we jump to the uh, final structure, but this is what you're going to do first. All right. First, just put an intermediate product here and then operating unit. So not yet the complicated one that I showed you. Okay, and then copy the properties that you can see here for the um, intermediate and the operating unit. So here, and then I change the problem settings. You may change the start default values in the measurement unit. Okay, and then solve the MSG and SSG and ABB. And you should be able to determine that the intermediate cost is 0 while the cost of operating unit 2 is 20 times more than operating unit 1, as you can see here. Okay, so you should be able to get the same solution as this one. Next, um, the flow from the intermediate is negative for operating unit 1, okay, since it's an input, and positive for operating unit 2. Let's see. So this is negative for operating unit 1, and it's positive for operating unit 2. So not shown, but so wait here, intermediate input, okay. And then you will have to click there here, and you can see uh this is positive for OU2. Okay. Next is export the details of feasible structure 1, and you should have the same result as here. Uh, the positive cost, it means it's not profitable. Okay, this positive cost not profitable. The negative cost means it's profitable. So please check as well the materials and the operating units tab. Okay. Next, but if there's no cost to produce an intermediate material or resource. So please copy the detail right here. Okay. And then please copy, make sure that you're the same. And the capacity multiplier is increased to its maximum to minimize the cost because the price of the intermediate becomes insignificant. So please follow that, make sure that you get the same uh, result. What if there's no constraint in the main raw material and product? So also try that. And lastly, what if there's no price in the intermediate and no cost in the operating unit? Okay, so please try the different scenarios. And then finally, add a resource constraint. Connect these two and add a resource constraint right here. Resource constraint. And make the price of the product 10 times of the original. So anyway, I will send you these slides, this part. You can follow on your own and make sure that uh, you're getting the same answer. Okay, so one by one, you can try it on your own. So how about you try also doing this structure? Okay, so after building that, creating here and linking the two, try changing the colors. Okay, so um, just to differentiate between a single operating unit node having three inputs, right, compared to a uh, model with three operating units. So you can check the difference in the mathematical representation and graphical representation. So try to do that also as well. Okay. And you will see that um, you will have four feasible structures. All right. So these are not required. What I will be requiring is this last exercise. Okay. So those are just your practice exercises. So you have to do a case study with three biomass and two demands. Okay, so just like our exercises in Lingo. So in uh, mathematical programming, this is the code for that. What you will try is to represent it in P graph. Okay. And you should have, in mathematical programming, this is the answer. You should get the same, right, the same answer as when you graph it in P graph. Okay, so try it. I will send you the uh, the file. Also try case study 2, this one. Okay, and then case study 3. So once you're able to do the case studies, then answer these questions. Okay. So your homework is case study 1 to case study 5. Let's move to the concluding remarks. P-graph generates the maximal structure of combinatorially feasible networks, optimal and suboptimal networks. Can be used for green supply chain problem, and it's demonstrated using case studies on sustainable energy supply and carbon management networks. All right, so actually that ends the lecture on P-graph.